Welcome to another video for Stat 212. In this video, we're going to talk about the normal distribution, which I feel like most people have heard about a normal distribution before they've taken their first statistics class. So hopefully we'll put a nice broad conceptual description on what it is, why we see it, and how we kind of use it a little bit. So a normal distribution is just a very common distribution to see in nature. Now, I want to clarify though, it doesn't mean that there's something wrong with distributions that are not normal, right? So it's not that other distributions are abnormal or non-normal. I mean, I guess in a technical sense we could say they are, but there's nothing wrong with non-normal distributed data. So just kind of keep that in mind as we move through the course. That data can take any distribution, it can take any shape, and it has its complete right to do that, right? So we want to, this is an inclusive statistics class. We don't judge distributions by their shape. We just welcome them and analyze them the way they are. That said, we will see lots of normal distributions, and we should know a few properties about them. So normal distributions are often based on a probabilistic pattern where there's going to be kind of a center, there's going to be kind of a common value that data values are going to be very close to, and deviations from the mean become rarer and rarer to see the larger the deviation becomes. So maybe a good example for normally distributed data would be in quality control of products. So here we have an example talking about boxes of Cheerios. So if you think about a machine that's going to be filling up a box of Cheerios and how many Cheerios go in there, there's going to be an average amount that's typically going in that box. Let's say it's 21 ounces. However, if we're measuring it very precisely, we're going to find that not every box of Cheerios is the exact same weight. There's going to be a little bit of variation in Cheerio box weights depending on exactly how many of those Cheerios came in, exactly how perfect those Cheerios are, and things like that. So we're probably going to see a distribution normally distributed around 21, and the farther away from 21 we get, the farther from 21 we get, the rarer it is to see a box of Cheerios at that particular weight. And so there's a lot of different situations that we can kind of come up with where data is going to be normally distributed. So it's good to see it. We're also going to use it a lot in inference, and we'll talk about why when we get to the next chapter, talking about the distribution of a sample statistic. So because data often takes this shape, and because we often use it in inference as well, it's good to know kind of the percentages associated with the normal distribution. In other words, given the mean is this, and given the standard deviation is this, what percentage of the value should be within different ranges, right? So we could do it for the uniform distribution, and that's usually pretty straightforward because it's uniform. But if it's this normal shape, there's some probabilities that go with it that is generally good to remember. As a first step, though, before we get there, let's talk about standardization. So standardization is a way to kind of convert values to a common scale that we can use in different contexts. So if you think about this idea of standardizing, let's say that you have, if we're talking about like an SAT scores versus ACT scores, maybe some students only take the SAT, maybe some students only take the ACT. So for college admissions, what they often do is they have a way of kind of standardizing those scores to a common measure, so that an ACT and an SAT score can be kind of compared equivalently in terms of its percentile rank. So with that in mind, if you think about different variables that are normally distributed, that are measured in different units, that are talking about different things, it can be helpful to convert those values to a common scale that we call the standard normal distribution. And the standard normal distribution is going to be centered with a mean of 0 and standard deviation of 1. And so what we do is we just convert the units to z-scores or z-values. Either term is fine. We convert those data values to z-scores, and then we can talk about how likely we are to see a z-score above 1 or a z-score below negative 1.5 and different things like that. And no matter what units we're talking about, no matter what data we're talking about, if we've converted it to a z-score, we're talking about the same thing, and we have the same standard percentages associated with these values. So z-values that are below the mean are going to be negative. And z-values that are above the mean are going to be positive. And a z-value of 0 means that that data point is exactly on the mean. Okay, so let's look at some examples here. So there's a visual, first of all, of what we just kind of said there. And then this is how we would convert a data value to a z-value. So we're going to take our observation, our particular data value, minus the mean, and then we're going to divide it by the standard deviation of our variable, of our data set. Or not a data set, but the variable of data, the data we're looking at. Okay? So as an example here, we have some z-values for some heart rate data for newborn babies. And so apparently there's a distribution of heart rates that we see for newborn babies. And these 6 babies have been kind of extracted from that data set for us to kind of compare. And so we notice that some of these babies have heart rates that seem to be below the mean, some are above. So our first question, how many babies had heart rates that were below the mean? And I would just notice how many of them have negative z-values, which appears to be 1, 2, 3, 4 of them had negative values. So that means that 4 of them were technically below the mean heart rate for newborn babies. Which baby's heart rate was closest to the mean? So that's going to be the one that's closest to 0. So in this case, Rachel has the one that's closest to the mean. She is ever so slightly below the mean. She has 0.04 standard deviations below the mean. And then there's another question. Babies with a heart rate far away from the mean should be monitored for heart problems. Which baby might need to be monitored? So if I'm thinking about which of these z-values signals that the data point is far away from the mean, it looks like it's probably going to be Dylan, because Dylan's is 2.52 standard deviations above the mean. So that is pretty high. And we'll talk about later how we decide how probabilistically unusual that z-value is going to be. Let's say that the mean heart rate for newborn babies is 88 beats per minute with a standard deviation of 10. What would be the z-value for a heart rate of 94? So the question that I'm asking here is how many standard deviations above the mean or away from the mean is 94? And I can do that by finding the raw distance from the mean and then dividing by the standard deviation. So I'm going to get 6 over 10, which is going to be positive 0.6. So 94 is 0.6 standard deviations above the mean, right? So I can kind of see that here where 94 is 6 units above and its standard deviation is 10. That's going to be 0.6 standard deviations above. If the heart rate was 98, that would be a z-value of 1. That would be exactly 1 standard deviation above the mean if the standard deviation is 10. And if the heart rate was, let's say, 73, that would be 1.5 standard deviations below the mean, because that would be 10 plus half of 10 would be 15, so that would be 1.5 standard deviations below the mean of 88. We can also plot z-values on a density curve by drawing a z-scale below the normal distribution here. So here we have a normal distribution density curve. So then if I were to draw a z-scale down here, then the middle, the mean right here, would be associated with the z-value of 0. And then if I go down, these are going to be negative z-values. If I go up, these are going to be positive. So I'm going to do about -1 right around here, -2 around here, +1 around here, and then +2 around here. And usually the 1 standard deviation points are going to be around the inflection points. I just kind of mentioned that as an FYI there, because a lot of times in stats, if you're drawing a density curve, which we won't do a whole lot in this class, but every once in a while we will, The 1 standard deviation marks typically should line up with where these inflection points are. So the inflection points are where the direction sort of switches, where we stop going sloping down and we start sloping less down again. Okay. So here we have another practice question where we have IQ scores are designed to be normally distributed with a mean of 100 and standard deviation of 15. That is true, by the way. At least I think it's true. Maybe off by a couple numbers, but I think that's right. And we're going to draw a normal curve to represent, well, it's already drawn, to represent this distribution. Label the mean and values 1 and 2 standard deviations away, and draw a z-scale. Check, we've already done that. So if that's the case, if the mean is 100 for this variable, then we're going to put 100 right around here. And then the 1 and 2 standard deviation values are going to be 15 below would be 85. 30 below would be 70. 15 above would be 115. 2 above would be 130. Okay, so you can kind of see how it lines up with those z values. And so, right, so we have our one particular variable of interest, which is IQ scores, and we can represent this distribution with a normal distribution, with most people scoring around 100, and the farther away from 100 we get, the fewer scores we see in those ranges. The z-scale here allows us to standardize those values to a common scale. So it doesn't matter what variable we're working with, it doesn't matter what the context is, we can always convert a normally distributed variable to a z-scale. We can standardize it, and then we can make some comparisons between different distributions with different units, and we can use probabilities of the normal curve much more easily, as we'll see in the next section. First, though, let's answer a couple more questions here. What is the z-value for a score of 94? So again, you might want to pause the video and try these on your own too at this point, but I'll go ahead and solve them here. 94 minus 100 divided by 15. So again, it's going to be x minus mu over sigma. And that's going to be negative 6 over 15, which is going to be negative, let's see, 369, that'd be negative 0.4. So this is going to be 0.4 standard deviations below the mean. And then a z-value for a score of 106, that's going to be 106 minus the mean divided again by the standard deviation. So I'm going to be here 0.4 standard deviations above the mean. So notice that those scores are equally distant from the mean. They're just in different directions. But they're going to have the same z-score because they're both the same distance from the mean. They're both 0.4 standard deviations from the mean. It's just that one is negative and one is positive to indicate direction from the mean. And then last, we're going to shade the area on the curve that represents scores 6 or more points away from the mean. So I'm going to kind of put 94 somewhere around here. Maybe I'll use a different color. So 94 somewhere around here. And 106 is going to be somewhere around, I guess about here. And, you know, I'm probably not the most precise drawer because I feel like I don't have exactly the center sector there, but hopefully you'll forgive me for that. And I'm just going to shade the area of the curve, representing scores that are more than 6 points distant from the mean of 100. So that's obviously a good chunk of the curve. I mean, obviously there is a sizable portion that's included in the middle here. However, it does appear that most people are scoring more than 6 points away from the mean. And as we'll talk about in the next section, we can calculate those probabilities for any given range under the normal curve. As long as we can easily convert it to a z-score, there's some normal percentages that are going to help us out for that.